So, this is an introductory course in algebraic geometry. So, this is a introduction to is the aim of this course to introduce the basic notions and concepts in the subject, and at the end probably we will prove few theorems, some basic theorems. So, the aim of this course to introduce basic notions or topics in this subject in algebraic geometry. I write is that AG, and at the end and prove some basic theorems. So, what theorems we will prove? We will target, for example, there are, for example, Bezout's theorem. One of the it's one of the very basic theorem which says something about intersection of curves, or in more generally intersection of varieties. So, and and we will see how far we can go. But to as you know, as we will see that to introduce basic topics, it will take some time. So, you have to be little patient initially to see the end product. Okay. So, the plan I have uploaded in the Moodle website, but still I will just say few weeks from now onwards what I am going to do. So, next few weeks I am going to do. So, first week and second week I will mostly talk about some commutative algebra results, which I require. I mean, without that I cannot do anything. Week 1 and week 2. So, I will mostly recall or some proof and give a sketch of proof of some commutative algebra results. So, recall some commutative algebra results with a brief sketch. With a brief sketch of proof. And I assume that in commutative algebra, you know what is rings, what is module, what is a localization, what is tensor product. So, these things you know. I assume this. Okay. So, what kind of so first so we will talk about integral extensions. This is so. Let's start integral extension and some related results like going up, going down theorem, Cohen-Siedenberg, this is known as Cohen-Siedenberg theorem, and which is very important. So mostly I will these are the important topics which we need. We will use a lot. So, going up and down theorems, and then the Noether normalization. This is another important theorem. These are basically two important topics in this commutative algebra chapter, which are used very extensively in algebraic geometry. Noether normalization theorems. And And then next is I will talk about valuation. Okay, and after that, so this is how I will. And then the third one, I will talk about the rule dimension theorem, which will be used. So it has major use in. So whenever you are interested in computing some dimension of the underlying variety, this rule dimension theorem will play a very important. So these three topics mostly I will talk about in coming weeks. So let's start with integral extension. So first of all, we are doing commutative algebra. So all our rings are commutative and with identity. Okay, we assume. So from basic, all rings are commutative with identity. So suppose you have a let P be a ring and A be a subring. Okay, before that I should say whatever I will say today, you can find it the reference for today's class. You can look at Atia MacDonald chapter 5. Everything is there. So if I miss some point, probably you can look at the book. Okay, so let B be a ring and A is a subring of B. So now definition, I put a let X belongs to B, a element in B, and X is said to be integral over A if X is a root of a monic polynomial with coefficients in A. So that is X satisfies equation x to the power n plus a1 x to the power n minus 1 dot a n equal to 0 with ai belongs to A. Right. So in particular, if x is an element of A, then x is integral over A, because you have the if x minus A equal to 0, it satisfies the monic polynomial. Okay. So example, whenever we think of example in commutative algebra, we go back to the basic example, that is a ring of integers. So you take A to be Z and B to be Q. Now you from the division algorithm, you will see that if you have an element of Q which is integral of Z, it has to be an integer. So any element, so that in other words, that Z is integrally closed in Q. So any element of Q which is integral of Z, it has to be an integer. So any, so you have to be little bit, you have to do little bit of work. So I will put a small exercise here. Check any element in Q which is integral over Z has to be in Z. Well, it's not difficult. We will see plenty of examples where this is not the case. Okay. So once you have a definition, then you can ask that, okay, if I suppose B is a ring containing A. Now, if you take a set of all integral elements of B in A, so what kind of algebraic structure it has? It turns out that it has a ring structure. If I take integral elements of B in A, it forms a subring of B. It may not be the whole, of course, it has to contain A. So, it will be some kind of ring extension of A, intermediate ring, yes. So, it will be an intermediate ring between A and B. So to prove, so how do you prove that such that you consider all integral elements, they form a ring, they form a, it's a subring. So to do that, we need a following important first proposition. Proposition 1. So the following are equivalent. First, A and B as before, x belongs to B is integral over A x. When I write Ax means the polynomial ring with coefficients in A. Okay. So Ax is finitely generated A module. Okay. So Ax is, of course, is a finitely generated A algebra, right? But it's not a finitely, in general, it's not a finitely generated A module, right? But what it says that if x is integral, then Ax is finitely generated A module. Three, there exists a finitely generated A module C containing A and sorry, not A, Ax, and so this contains the ring Ax and B C such that C contains Ax and C is contained in B. Okay. there exists a faithful AX module M which is finitely generated A module okay. So, first statement is if something is integral over A, definition is clear. Second one is also clear that AX is a ring and it is finitely generated A module. Third one is there is a finitely generated A module C. So, a priori you do not know AX is a finitely generated A module. So, you consider the ring AX and what it says that you have a finitely generated module C which is you have a subring C which is inside B which is finitely generated A module and which contains AX. And the fourth one is this faithful AX module. So, faithful means that whenever you have a, so let us recall what do you mean by faithful. So, suppose M is a R module, M is an A module, say A module, this then M is faithful if for every A belongs to A, the map phi A which sends the R linear map which sends M to AM phi A is not 0. For every A of course not equal to 0. If A is 0 then everything is 0. So, if I take a non-zero element in A and consider this translation map, left translation, which sends a M to AM, then this is a non-zero map. That means there is at least one M such that AM is not 0. Okay, this is called faithful. Now, following these four statements are equivalent, and as a consequence, you will see we will prove that ring this set of all integral elements of B over A is a ring. It forms a ring. It has a ring structure. First of all, how do you? So first, x if x is an integral over A, then Ax is a finite. This is a very easy consequence because you have some polynomial x to the power n, right? So I will just write briefly. So proof or sketch 1 implies 2. This follows from the fact that you have some expression x to the power n, you can write it as a1 x to the power n minus 1 up to a0, right. So, because of this fact, any Ax is this Ax is a finitely generated A module. Is it clear? Okay. So, now next is what is the next one? Next one says that there exists a finitely generated A module C such that Ax contains C. Okay. So, you know the Ax is finitely generated, right, already. So, you take C to be Ax.
So, basically in second proposition you are saying that the entire Ax is generated by one x square xn up to xn minus.
Yes, they are the generator for Ax.
Up to xn minus.
Yes, correct. So, next is So there exists a finitely generated A module which contains AX. So you know AX is finitely generated, right? So you take C to be AX. 3 implies 4. What does it say? There is a faithful AX module M which is finitely generated as an A module. Here also you take M to be AX. Right. So only tricky part is 4 implies 1, and which is crucial. So that means that if you have a faithful AX module M which is finitely generated as an A module, then X is integral over V. X is integral over A. So this is the tricky part. So this is to prove this. I will just give a brief sketch. You have to use Cayley-Hamilton theorem. This follows from Cayley-Hamilton theorem. You remember Cayley-Hamilton theorem? You have some if you have a map from a finitely generated A module to itself, then it satisfies some monic polynomial. You have to use that. Okay. So you consider this map X going from M to M, multiply by X, and use Cayley-Hamilton theorem. I just leave it as exercise. I don't want to go into detail, but you have to check the condition of Cayley-Hamilton theorem. There are some certain conditions, right? It has to be finitely generated and they satisfy it. Okay. Sorry. But as a corollary, you see now, suppose you did it for only one element X, you can do it for multiple elements. Suppose x1, x2, xn belongs to B are integral over A then you consider the polynomial algebra in x1. So, polynomial ring you know, but now you consider multi-variable polynomial ring. So, then A x1, x2, xn is finitely generated. A module. So, this proof follows from induction hypothesis. So, how? For when n equal to 1, so when n equal to 1, it is already proposition 1, follows from proposition 1. When n greater than 1, you use induction hypothesis. How do you use induction hypothesis? So, suppose you write A r as A x1 x r. R is from say R1 to n. Okay. So, now notice that this is nothing but A r minus 1 x r, right. Now assume by induction hypothesis, it is a induction hypothesis AR minus 1 is finitely generated A module. Now x, which is the element of B, is integral over A. So this will imply that x is integral over AR minus 1, because AR minus 1 is a ring containing A. If something is integral over A, then it is integral over the bigger ring. So this implies AR, which is nothing but AR minus 1 by, again, the previous proposition, is integral, is finitely generated AR minus 1 module. So we have this AR minus 1 and this is AR. AR is a finitely generated AR minus 1 module. AR minus 1 is a finitely generated A module. So this implies, so this is finitely generated, this is finitely generated. So this implies AR is finitely A module. Okay. Okay. So as a remarkable consequence, now you will see that the set of all integral elements are, they form a subring, right? So corollary, as a corollary, you will see that the set C of elements of B, set C of elements of B which are integral over A is a subring B containing A. Proof. So to prove something is integral, what you have, something is a ring, what I need to prove? I have to prove that x, if x, y belongs to C, to show if x, y belongs to C, then x, y and x plus minus y, they are in element of C. Then it will be a subring, right? So, but you see that AXY AXY is a subring of AXY, right? And similarly, AXY, x plus minus y is a sub of AXY. So this is A, you know, AXY is finitely generated, A module. So these subrings are finitely generated, right? A module. But now you use proposition 1 to say that if something is finitely generated, then that element is integral element. So now you see that why I wrote so many equivalent statements. 1, 2, 3, 4. to prove that Ax is finitely generated A module, to go back to that x is integral over A, I require those 3 and 4 basically. So that Cayley-Hamilton theorem is a very important, you see that Cayley-Hamilton theorem is a very important application in this case, that set of all integral elements of B over A forms a subring. So, this is a major application of Cayley-Hamilton theorem. Okay. So, I will stop here and I will wait for questions now.